Hi, everybody. Thank you very much for coming back after lunch. My name is Michael Wong. I'm with CodePlay. We're presenting this talk in consortium with a number of people who have been involved in parallel programming for a number of years, and we definitely have the gray hair and the lack of hair to show for it. My colleagues are Paul McKenney from IBM and Maggot Michael from Facebook. So you're definitely getting a cross spectrum of probably, I would say, at least half a century of experience, I would expect. The topic of our discussion is going to be about, it's somewhat controversial. We always believe, or you've always heard, that parallel programming is hard. So what should you do about it? We are turning that a little bit, and we're saying, is it still hard? Because if it is, we need to do something about it. Again, so as with any talks, it's supported by a number of people in the background, various standard committees, various discussions that we've been having. With anything, I would say that there's always going to be some amount of errors, and anything that remains is all mine, not anyone else's. I would like to say it's all theirs. I would like to think that all of the good stuff is all mine, but that's unfortunately been proven too often not to be the case. Finally, there's a usual legal disclaimer. I won't bore you with it. It's a standard template. And of course, the thing that my company always makes me put on, not a bad thing really. It tells us that our company does a lot with heterogeneous computing in C++, with a language called SYCL, which we're trying to put into the C++ standard. So today, what are you going to hear about? We actually have three speakers. Hey, Anthony. Don't you hate it when you walk in and people call out your name? It's okay, we're good friends. The business is such that you kind of know everybody by now. You know all the parallel programmers, practitioners who's been in it around for all these years. So our topic is separate out into three groups. I'm gonna bring in the preamble about asking you, is parallel programming fundamentally still hard? And I'm gonna show you because we've been involved in designing parallel programming models for almost 20 years. We've had some experience and background in understanding where the fuzzy edges are. So what does it mean to have to be designing a parallel programming model? Paul McKenney is going to come in and look at the hardware side. Look at from the hardware side. Can it actually help? Can it make parallel programming easier? And then Maggot Michael is going to come in and give you a really detailed example, just so that you don't say, well, we didn't see any code. Well, there is code, but it's coming, okay? And it's not going to be just any code. It's not just going to be any little blob that you're going to fit into a single slide. It's going to be about a detailed breakdown about single producer, single consumer buffer. And it's going to show you all the things we're going to talk about from the previous two groups, talking about fault sharing, parallelism, about locality, atomic operations, and cache line bouncing. So, we figured this talk is aiming at a mid-level of parallel programming, not necessarily a total beginner level, and not necessarily at the more advanced level that we usually talk about. So as a result, we're not going to talk about lock-free programming. We're not going to. I usually come up and talk about transactional memory. You're not going to hear any of that. We're not going to talk about hazard pointers or RCU. We're not even going to talk about computer architecture, although many of the things on this screen are kind of required reading, you know. But this is one of those things where the person on the stage is asking you to go do your homework to some extent, because it would be boring for us to actually go through all these things. In fact, we actually have slides for all these things. We weren't quite exactly sure where to draw the line, so we actually did all the slides, and over 200 of them, and then we threw them all away this morning. Have you ever had that happen? You know, that morning you're like, we don't have time for it. No, this is all gone. It's really good stuff though, I promise you. You would have been really impressed when you look at the stuff that we have talking about Flynn's classification, talking about dependencies, talking about parallel patterns. These are all exciting topics, but they're not for this talk. They're for other talks. Maybe other people's talks. We have actually talked about them in some of our talks, like transactional memory, RCU, hazard pointers from previous years before. All right. So when you talk about parallel programming, a number of parallels comes to mind. People talk about them all the time. And we definitely have the gray hair and or the lack of hair to show for it because we've been doing it for over 20 years in some form or another. I myself was started over about, because of my involvement at IBM and as an IBM scientist, we were doing high performance computing. I was the CEO of OpenMP, so we worked hard to develop the OpenMP, which is a parallel compiler on top of C, C++, and Fortran. So we met all these things at some point in time, whether they were data races or mutual exclusions or locks. What happens if you have contention that would lead to poor scaling? What happens if you have false sharing? That was probably the first thing you run into. Okay, and then there's also poor lack of locality references, lack of load balancing issues. They all lead to some consequence or another. And certainly with communication overhead, that just causes everything else to go bad. I'm going to, as with any talk, I just want to step back very briefly to talk a little bit about not a whole lot of time, because I think many of you guys may know anyway. But certainly you can see that by this chart, the growth of transistors is pretty linear and consistent over the last many, many years. However, the frequency clock has leveled off. And the only way to keep that speed, that speed promise that the vendors have, which is what keeps you hooked to buying their computer systems, is to continually raise that core. Okay? The problem is that even that has a problem, because very soon you run into this heat death of your system, and you've seen this before. This is essentially the free lunch, where the free lunch used to be, you just keep adding, you just keep buying new hardware and you get the free improvement. Now the reliance has to move into your software, because the hardware has stopped getting faster, so your software now has to get faster. This leads to exactly the same graph, except you'll notice that I've added the yellow line there on power. What has essentially happened is that a hardware problem is now just became a software problem. Like a lot of things in the world, bottlenecks just move from one place to another. Okay? And this is what's driving the parallel computing architecture today. That's it. Now, I'm sure all you guys have a car or know what a car does, but have you ever been in one of the really old Model T Fords? Okay, that's what it looks like inside. It would not be impossible for you to drive it. You could probably figure it out, but the controls aren't exactly what you're used to. For instance, the left side levers sets the rear wheel parking brake and then puts the transmission into neutral. The right lever is actually the throttle. Okay? And then the lever on the left of the steering column is for ignition timing. And then the left pedal changes to 2 forward gears, while the right pedal, the center pedal, controls reverse, and then the right pedal is the brake. Now, at one time, the ability to drive a car was actually only for very few people. But now it's fairly commonplace. This drastic change come about for 2 very basic reasons. Okay, the cars become cheaper and are more readily available, and the cars simply became a lot easier to operate because they have a lot of assists for you right now. A lot of automatic transmissions, automatic chokes, a lot of automatic starters, and they have greatly improved reliability as a result. And today, I bought this car about 2 years ago, and it's now basically the classic bloatware. I actually have stuff in there that I still don't know what it does. This is the manual that tells me what it does. I think it can steer itself through the lanes and all those things. Never actually used it. Half of this stuff is bloatware. I can still drive the car fundamentally without any of this stuff, but basically this is a little bit of what's going on in terms of technological domain. And it happens to computers just the same. It's no longer necessary, for instance, to use the key punch. I actually started by using a key punch in order to program. Spreadsheets now allow programmers, non-programmers to get results from the computers that would have required a team of specialists from before. Okay. One of the most compelling examples today about this ease of use of computers, of course, web surfing and content creation. Believe it or not, content creation would have required a team of scientists years ago. Today, we just hack together these slides. Paul lives in Oregon, actually. I'm in Toronto, but if I'm actually in Toronto, Maggot is in New York. Okay, and we've been working at this for the last couple of months, slowly putting it together. It's amazing that this stuff is actually coming together, and it's fairly taken for granted now. Years ago, this would have been a research project. So we're saying that the same thing is happening with parallel programming. If you argue that parallel programming is difficult, it's mostly because it's currently being perceived by many as being difficult. Let me explain what that means in some ways, because one of the things that, you see, computers have always been pretty much parallel. But what's going on for the last 20 or 25 years, all the languages that's been given to us, we've been forced by those languages to think serially. When you create a loop, for instance, even though you know innately what happens, it loops around, there's actually a lot of force ordering that is actually implied in there beyond what it's actually doing. A lot of those things are unnecessary. In fact, they're harmful for parallel programming. But the compiler cannot know those things. And this is indeed one of the reasons why that in order to think parallel, you do have to go back to the reality of it. Okay? All of you guys can drive and do a lot of things in parallel. All of you guys can work your car while texting on your cell phone. I know it's not legal, but I'm sure you all do it, and I do it myself. Okay, that's parallel processing right there. Yet with computers, somehow we're forced into this perception and not your fault, I would say, of years of this guidance that we should try to think of things in terms of steps of serial operations, when it really is not necessary. And this is actually what's causing the perception that parallel programming is difficult. It's not parallel programming that's difficult. Programming itself is difficult, period. Okay? Whether it's serial or parallel, but you've been all trained to make serial programming a lot easier. Okay? So if you look back at many of the historical difficulties, you'll see that historically, there are many of these difficulties, these problems that are well on the way to becoming overcome. First, over the past few decades, the cost of parallel systems have decreased tremendously from many multiples out of a house to a fraction of that of a bicycle. In fact, I dare you to find something that is not used, that does not have parallel processors today. Okay? So the second thing is that the advent of low-cost and readily available multi-core systems means that the once rarefied experience of programming parallel systems is now pretty much available to everyone. This is pretty much the same process as an automobile in a way. It's well on its way of being common for everyone to be able to do these kinds of things. Third, in the 20th century, there are large systems of highly parallel software that was pretty much closely guarded proprietary things. Today, on any GitHub, you can easily be participating in a parallel programming project. The fourth thing, even though the large-scale parallel programming projects in the 80s and the 90s were almost all proprietary projects, these projects have essentially seeded a community with a massive group of developers who understand the engineering discipline that would be required. So that actually helps to take us to the fifth part. Unfortunately, the fifth part is the one that is still a problem. The high cost of communication relative to that of processing is still largely in place. And this difficulty is essentially has been increasing every year, actually. So the onus, I would claim, is that if you believe parallel programming is difficult, the onus is on you to come up as to the reason why. If you really believe that it's exceedingly hard, then you should have already some kind of an answer as to why is parallel programming hard. And indeed, you could list any number of reasons, ranging from the things that I've shown in previous screens, like deadlocks or race conditions. The real answer I've already mentioned is that it's really actually not all that hard. If it were all that hard, then how is it possible that we have all these large open source projects on Apache with MySQL, on Linux kernels, for instance, and people have been able to do that? Okay? So a better question might be, why is parallel programming perceived to be so difficult? So how could parallel programming ever be as easy as sequential programming, you might ask? Well, it really all depends on the programming environment. If you heard of the programming language SQL for databases, it's a really underappreciated success story, because it really allowed programmers who pretty much know nothing about parallelism to keep a large parallel system productively active with a fairly easy command that is very English, that is very much English-like. MATLAB actually does something very similar. And then on Linux systems, take a look at the command here that I've written using a get input with a grep and then a sort. In this case, the shell essentially runs a pipeline. The shell pipeline essentially runs the get input grep and then sort the process in parallel. Now, this is a parallel system right there. It wasn't that hard. So in short, I would say that parallel programming is just as easy as sequential programming, at least at these environments that hide the parallelism very well. So after years of doing designs, doing language designs, some of the things that the three of us have considered are the design points that makes for a good parallel system. So the goal of parallel programming over and above sequential programming are these three in general. You have performance, you have productivity, you have generality, okay? Actually, that's a mistake. Portability should really go with productivity. But what it does form is this well-known iron triangle that if you are a team leader of a project, you will probably have a lot of experience about balancing your teams and the tasks that needs to be done in terms of resources, in terms of time, in terms of personnel. So when you're designing a language, any language, you have these things to consider. Now, you may not actually be thinking about them. In fact, most designers probably are not. When you're examining a parallel programming language, you could usually use something like this to characterize it and see where the design points are, whether it's giving more favor to performance, whether it's giving more favor to productivity or generality. So what about, some people might ask immediately, what about correctness, maintainability, robustness, and so on? Now, these are important goals, and they're just as important for sequential programs as they are for parallel programs. And because of that, we claim that important as they are, they don't really belong on the list that we're looking at for parallel programming. And if correctness, maintainability, and robustness don't make the list, why do productivity and generality? Well, given that parallel programming is perceived to be much harder than sequential programming, productivity essentially is tantamount, and therefore cannot be omitted. High productivity parallel programming environments like SQL, they serve a really special purpose. So generality has to also be added to the list. Are they specific? One of the reasons that they are high productivity is because they're very specific and very good at what they specifically do. And that gives you a clue about language design. The more general something is, it's going to be much more difficult for it to serve a multiple large audience of needs. But there's good reason to have general purpose languages. you wouldn't be here if you didn't know about that, because C++ is one of the best general purpose language there is. Now, given that parallel programs are much harder to prove correct than sequential program, you might still say that correctness really should be on the list. Now, from an engineering point of view, the difficulty in proving correctness, either formally or informally, would be important so far as it impacts the primary goal of productivity. So in that case, correctness proofs are important, and they're part of what productivity would be. And finally, I know that a lot of you guys are general hobbyists. C++ is something you love, you're interested in, but it might not necessarily be your day-to-day job. So having fun, so what about just having fun with C++ or any particular language? Well, having fun is important, but unless you are a hobbyist, you would not normally be a primary goal. But if you're a hobbyist, go nuts on it. Let's take a look at the first criteria of performance. So the focus of performance has shifted from hardware to parallel software. This change is basically due to Moore's law, because it continues to deliver increases in transistor density. It's basically ceased to provide the traditional single-threaded performance. So as you can see in this picture here on the side, which shows that writing single-threaded code and simply waiting a year or two for the CPU to catch up is no longer an option, then given the recent trend on the part of all the major manufacturers, parallelism is the only way transferring the hardware problem into the software problem. Even so, the first goal is performance rather than scalability. Given that the easiest way to attain linear scalability is to reduce the performance of each CPU, given a 4-CPU system. Let me give you an example. Which would you prefer? A program that gives you 100 transactions per second on a single CPU? Or a program that gives you 10 transactions per second on a single CPU, but scales perfectly? The first programs definitely makes a better choice. And even though the answer might change if you happen to have a 32 CPU system. What I'm trying to say here is trying to bring you back down to the base case. People are often too eager to start using parallel programming right away, because we're all involved in it, and our heads in it. But just because you have multiple CPU doesn't necessarily mean that in and of itself is a reason to use them all, especially given the recent decrease in price of these multiple CPU systems. The key point that you want to take away from here is that it's just one potential optimization of many. If your program is fast enough to optimize either by parallelizing it or by applying any number of potential sequential optimizations, you should definitely go with the sequential optimizations first. Let's look at productivity, which is the next part. Now, productivity has been becoming increasingly important in recent decades. To see this, think about the price of early computers that were tens of millions of dollars at a time when essentially engineering salaries back then were a few $1,000s. If dedicating a team of 10 engineers to this kind of machine would improve its performance by even 5% or 10%, then the salaries would be repaid many, many, many times over. One such machine I'm not going to talk about was this Syserac, one of the oldest stored program computers there. But this computer had lots of transistors, was built with thousands of vacuum tubes, okay, requires an army to maintain. So today, it would be quite difficult to indeed purchase a machine with so little computing power. Maybe you could buy some 8-bit embedded microprocessors like a Z80, but even back then when we were buying them as a kid, you could probably buy them for I don't remember, like they were $2 for a couple of thousand units or something like that. So it really wasn't all that hard. Now, today with the advent of multi-core CPUs, this increase has allowed to be continued basically unabated, despite the clock frequency that we have been encountered in 2003. So perhaps the takeaway from this is that maybe at one time, the sole purpose of parallel software was performance, but now I argue that productivity is much more important than just performance. So one way to justify the cost of developing parallel software is basically to strive for maximum generality. All else being equal, the cost of a more general software artifact can be spread over more users than that of a less general one. Unfortunately, generality often comes at the cost of something else, and in this case, one of the iron triangles, either the performance or the productivity, or both. Now to see this, think about a few popular languages. If you look at C, C++, locking and threads, something we created for C++ 11, okay? This which essentially is based on POSIX thread, Windows thread, or some kernel threads or something like that, they essentially give you pretty good performance and very good generality, or in this case, portability, but it's still not very productive to program in that manner. We've all pretty much been told that you should not program in raw threads. You should use some higher abstractions instead. However, I argue that with C++ 14 and 17, these days, we hope that we're designing something that can give you a choice in that iron triangle. If you start using higher level abstractions of task, higher levels of parallelism TS, using the parallel algorithms, or higher levels of the concurrency TS, which we hope will be coming for C++ 20, what happens then is that you can now start tuning, give you a little more tuning of the knobs as to whether you want more performance, or whether you want more generality, or more productivity, more portability. That's the real key that these new C++ parallelism capabilities are really giving you. Now, you can all get down into the mud and talk about the fact that the parallelism TS allows you to do vector and parallel and vectorized, or just or parallelized. At the end of the day, it's about the fact that you can essentially tune the knobs much better than before. And this is unique among programming languages. That's why these guys are in red. You heard Biana this morning talk about Python. It's probably clear that Python is a high productivity language with great generality. And in fact, in this particular diagram on the right here, the further down you get into the hardware level, the productivity generally decreases. It's getting more specific, okay? But you still, that is the point where you can start generally get better and better performance and better and better generality. So as a result, something like Java gives you great productivity and generality. This is a general purpose language, inherent multi-threaded capability, with a great garbage collector and a rich set of class libraries. But the performance generally has been acknowledged as being poor. MPI, the message passing interface that the scientific community uses for node-to-node parallelism, is something that has been around for a long time, and it generally powers some of the biggest computer clusters out there. It gives you unparalleled performance and offers scalability. So in purpose, it's pretty general purpose, but it's essentially mainly used for the scientific and technical computing. The productivity is, believed by many, is lower than C and C++. OpenMP gives you a set of compiler directives using pragmas or commands, and you can paste that over C, C++, and Fortran in the same way, which gives you this commonality. So it's, especially if you're doing mixed programming, which many of the people in national labs have. They might have some code in C. In fact, most of the weather code that is running, predicting your hurricane system, everything around it is actually C++ code, but the kernel is all still Fortran code. And nobody can change that because they've been debugged over 20 years. And if you try to change that, something will happen that is not going to be good. So as a result, this is the kind of mixed world where something like OpenMP really works well. And in this case, it is quite specific to the task that it's been set for it. Now, this specificity has a cost because it limits the performance in some ways, but it is definitely easier to use than MPI. Then we come to a language that supports heterogeneous computing, like OpenCL. It's run by Khronos, and they host a number of graphics initiatives like OpenGL and now Vulkan, and as well as the language SYCL later following on that. It's one of the first language that allows you to dispatch to any number of GPU devices that's not NVIDIA. If it's NVIDIA, then you have to use things like CUDA. It is also believed one of its major issue, not to say its downfall, but it's one of its major issue is that it's too low level. Okay? And because it's too low level, it's very low level, its productivity is not high. So as a result, definitely it falls in the generality and performance domain. Now, SYCL is actually the C++ language that is based on OpenCL that basically gives you the same ability. It allows you to dispatch to any OpenCL devices that's not NVIDIA, although that could actually happen fairly easily. So it also gives you great performance and generality. But because it's based on modern C++, it has the same capability allowing you to choose each point of that iron triangle. You could tune it for higher productivity if that is what you wish, if you believe C++ can give you that higher productivity. Okay? Finally, with SQL, the structured query language, it is probably one of the top language out there for relational databases. It's well measured by the Transactional Processing Performance Council using TPC benchmarks, so productivity is excellent. In fact, this parallel programming language essentially enables a lot of people to make good use of a large parallel system without having any particularly fine detailed knowledge about parallel program. These people do not know anything about fault sharing. They definitely don't know anything about lock-free programming or hazard pointers or transactional memory, and yet they're able to manipulate and get amazing results based on what they have. So it's important to note that a trade-off between productivity and generality has essentially existed for centuries in many fields. For example, in this particular case, a nail gun is more productive than a hammer because a hammer can be used for many things. If you have a hammer, everything looks like a nail, as they say. And so it should be no surprise to see that similar trade-off appear in the field of parallel programming. Here in this case, users 1, 2, 3, and 4 have specific jobs that they need the computer to help them with. And the most productive possible language environment for a given user is one that simply does that user's job without actually requiring any particular programming, configuration, or setup. Unfortunately, a system that does the job as required by user 1 is unlikely to do the job that's required by users 2. So in other words, the most productive language and environments are very domain specific. So by definition, they lack generality. Another option is to tailor a given programming language to the environment to the hardware system. For example, low-level languages like assembler, C, C++, or Java, or to some abstraction like Haskell, Prolog. So that is given or shown in the circular region in the center there. And these languages are considered to be general in the sense that they are equally ill-suited to the jobs that's required by users 1, 2, 3, or 4. In other words, their generality is bought at the expense of decreased productivity in that iron triangle when compared to domain-specific languages and environments. Worse yet, basically, a language that's tailored to a given abstraction is also likely to suffer from performance and scalability problems until somebody figures out how to efficiently map that abstraction to actual hardware. So with these often conflicting parallel programming goals, let's take a look at how to avoid these conflicts by looking at how to do them. So what makes it hard? These are essentially the aspects that you always have to go through as you're thinking about parallel programming. You would probably have to do some work partitioning, some parallel access control, some resource repartitioning or replication, or some interaction with the low-lying hardware. Okay? So work partitioning is absolutely required for parallel programming. If there's just one glob of work, then it can be executed essentially at most by one CPU, which is by definition a sequential execution. Now, the key point takeaway there is that and the thing is permitting threads to execute concurrently allow you to greatly increase the program state space. So this is about breaking up your work so that it can be partitioned, it can be balanced across these threads. The problem is that adding that very act adds to the amount of overheads and state space that you might be maintaining. And this is something you would have to decide. So as a result, this can greatly decrease productivity. Parallel access control essentially means given a single-threaded sequential program, the single thread basically has the full access to all the program's resources. These resources are things like I/O, memory, computational accelerators, files, and things like that. Now, the first parallel access control issue is whether the form of the access to a given resource depends on that resource's location. For example, in some of the message passing environment, local variable access is accessed using expressions and assignments, whereas remote variable access uses a totally different mechanism, these things called communicators. So the other parallel access control issue is how threads essentially coordinate access to the resources. This coordination is essentially carried out by a large number of synchronization mechanisms provided by the various parallel languages. Okay? And these things essentially can cause a decrease in performance because these traditional programming concerns like deadlocks, live locks, coordination can essentially is what is adding to your trouble with the performance. The third one has to do with resource, partitioning your data, your resource, and replicating across nodes. And this happens whether you're using a single CPU or multiple CPUs with GPUs. You have to move that data around. Data would have to be spread over numerous nodes or cache lines. Okay? Indeed, one of the biggest problems with heterogeneous computing, one of the biggest issues with heterogeneous computing is when and how to move that data efficiently to the GPU. So that it can be computed very quickly, okay, and worthwhile for the computation of the GPU, which often is in a SIMD manner. So resource partition is frequently application dependent, but it generally reduces generality because what happens is that in our research and work at CodePlay, we found that when we optimize that movement for one particular GPU, it doesn't work that great with someone else's GPU like AMD, or whether you might, and then none of that actually works with an FPGA, so you kind of have to throw your hand up and start over again. The last one has to do with interacting with hardware. At some level, you're going to have to know that. And hardware interaction is normally, while it's normally the domain of the operating system, the compilers or the libraries or other software environment structures, the developers working with new hardwares and components often have to work directly with them. And direct access to the hardware is needed because that's where you're going to squeeze out the last drop of performance. Yes, it's great to have all these great abstractions, but at some level, you still need that hardware interaction to do that. And direct access to the hardware is great, but it greatly reduces your productivity, especially if portability is required. So this gives you an idea of why these things are important and why every time you do parallel program, and we're going to demonstrate that later on with the hardware examples Paul's going to give you and the direct example that Maggot's going to give you in terms of how he's going to partition resources, how he's going to work with parallel access control. So at the end of the day, you've already seen the main theme I've been saying all along. The reason it's now easier to drive the car is because automation is there to help you. So I would say that with language and environments, automation is going to be the key for some of the killer applications. I've talked about this already at the beginning, so I've given it away. So what makes parallel programming harder than serial programming? A lot of this is just simply adapting a new mindset. Many of us drive cars, and many of our activities are in parallel when you play basketball, and yet we've been forced down this path by programming languages before us to think in a serial manner. The tools in front of us are guiding us into doing this in a serial manner. So if you look back, we can see that given the parallel systems have been in existence for decades, it's basically worth asking, why is it that they are causing so much fuss over the last few years? this is pretty much toward the end. I want to step back, given the fact that some of us have a perspective on history, and many of you guys do too if you lived through the 80s and the 70s. This was not the first great the great programming crisis. There was another one before, back in the 1970s and 80s, and eventually it led to a large number of languages, proliferation of language that was the good, the fad, and the ugly. Now, there were a lot of ugly languages and fad languages, and of the faddish languages that we had, I would say that some of them are things like Pascal, because essentially it's too bad. They held great promises, but had these weird type systems that you had to work with. None of it actually came to pretty much anything. They essentially gave you small advantages in some limited area, but essentially large disadvantages in other areas. When you look at the good languages, there were actually quite a few heroes back then. If you look back, you have, some of you guys might recognize VisiCalc. You might recognize a slide presentation manager. You might recognize the PDP mini computers there. These were back in the 70s and 80s, and they were the successful ones that allowed you to solve the programming crisis. The primary solution there was not based on not high-minded tools or languages, but rather the slowly processed spreadsheets, processors, presentation managers that essentially allow you to multiply your productivity 100-fold. You didn't have to write code in order to get any of that stuff done. You could essentially live through these useful helpers. So given that, and I've been talking about this for a while, I'd like to ask, what do you guys think is the most successful parallel programming language? What computer language that's used heavily in productions for decades essentially allows for developers to know nothing about threads, locking, or message passing, or anything like that, to keep a very large parallel system busy? Anybody have any thoughts there? Yeah, go ahead. Analog? Erlang, thank you. No. Yes, over there. SQL, thank you. SQL is actually one of the most amazing languages that we have. It's essentially one that gives you the high productivity. At the end of the day, it's all about either the language enable a large percentage of people to be able to use it in a very productive way, or itself enable a tremendous growth in productivity. Generally, the second part is much more difficult to achieve. So with that, I would like to pass this on to Paul McKenney.
Now we'll see if the adapters work. So I'm going to take it down a level a bit. We're going to go from programming models and parallelism into a little bit of hardware, software view of hardware. This is not a presentation to help you design your own computer. I'm sorry if you came here for that. I think there's other conferences that are into that sort of thing. RISC-V people and some other people doing open source hardware. Of course, my employer likes to talk about their hardware, but let's get on with this, if I can remember my password now, of course. Ooh, success. Okay, now let's see if we can convince this hardware to be productive, and see if I can find the right place to plug this in. Would be another step in the right direction. There we go. And, okay, something happened. There we go. Now let's try moving this over here. And let's try doing that. And it almost looks like something worked, you know? That's productivity, sort of anyway. Okay. So I'll be talking a little about hardware and its habits again, my website and a place to find more information on this. I'm going to kind of riff on one of the things Michael did. I'm going to say that premature abstraction is the root of all evil. Now, when I was growing up, when I was in my 20s and 30s, it was premature optimization. And in that case, we had these really old machines. A machine I used as a freshman in college had a memory access time of 1.6 microseconds. The clock was something like, what, 600 kilohertz or something like that, all right? And if you wanted the machine to do anything, you optimized first and asked questions later, and usually got in trouble doing that, which is why Don Knuth came up with that phrase that we all have heard. But this is quite a bit later. We have machines with much more power that instead of being refrigerator size like that one was. But you know, there's one thing we've lost. And I think this is something that is really important. The machine I was talking about, the one I used, that had the 1.6 microsecond access time, had little ferrite cores this big. The question I have for all of you is, why should you trust bits of memory that you can't see with your own naked eye? Okay, I mean, you really got to ask yourself about that. That's one of the things we've lost. Although having, you know, multiple gigabytes of it, 16 of them on this machine is kind of handy, I'll admit that. So, you know, there's something we've gained as well. So, one of the things about premature abstraction is there's some things that are difficult to abstract away, all right? It's hard to abstract away the finite speed of light. There was this thing about neutrinos a while back, but that turned out to be kind of a false alarm. As far as we know, we can't make the data go any faster than the speed of light, and we'll see there's other limitations as well. So you can abstract all you want, but the laws of physics are a little unforgiving. Now, one of the things we've done really well, one of the reasons that old machine I used as a freshman in college was so horribly slow, was it was big. I mean, if you think that it was bad that the little main memory were little cores about this big around, the registers were about this big, and they only had 12 bits in them. And so it took some serious time to get stuff from one end of that machine to the other, if, you know, being like this. This guy's got a CPU, and it's got 16 cores, excuse me, 8 cores. I'm not getting, maybe that'll be the next one I get. 16 hardware threads, excuse me, and the chip is only about this big. And so as a result, this thing can run at gigahertz, where the old thing ran at hundreds of kilohertz. And that's wonderful. That's something we've done. We've shrunk these down so that the speed of light is less of a problem. Unfortunately, there's other laws of physics that get in the way. That was exciting. Anybody want some water? The thing is that atoms are uncomfortably big. They're inconveniently large. 12 years ago, I saw a scanning electron microscope of a transistor. And the base, that's the part in the middle, and the thinner the base, electrically thinner, which is, think of it just as thin right now, is what controls how fast the transistors can switch. The thinner that base, the faster the switching. Well, 12 years ago, they had transistors in production that were about this many atoms across, 4 or 5 atoms across the base. They have made research transistors that look like that, where they have one layer of atoms for the base. Now, it is possible to split atoms. We've done that for a long time, but doing that kind of spoils them for electronics use in our experience, and for much else besides. Now, there are some other tricks that people are pulling. I mean, one trick is just not to have any atoms in the base. And believe it or not, there actually has been a research transistor constructed that does that. You just have the source and the base with a gap between them. It's actually a solid-state vacuum tube. I mean, it's really cool. The atmosphere at those scales is so thin that it's for all intents and purposes a vacuum. And so you make vacuum tubes out of semiconductors, except the way they did that was they made a huge pile of them on this chip, and a few of them worked. Which is a wonderful, I mean, it's a really cool demonstration of capability. I mean, don't get me wrong, but we need to have billions of them on the chip all working. And you kind of have to place the atoms, and well, maybe we'll get there sometime, but we aren't there right now. So for right now, we're kind of stuck with this. And that's kind of a problem. So here we are. This is kind of a cartoony picture of what a system might look like. We've got sockets with CPUs on them. They could be multi-threaded. I didn't show that here. There's some kind of interconnect. There's memory. The memory might be associated with the sockets or might be off on the side like we show here. There's a little bit of variety. The problem is, at 2 gigahertz, the speed of light going out and coming back is about that far. Okay, well, that's not so bad. I mean, you know, look at my laptop. You know, that's most of the laptop, right? And if you put all the stuff in the middle, shouldn't be a problem. Except that we haven't used vacuums for computers since I was very small. And I'm one of the guys Michael was talking about with the gray hair, all right? And I do have this honestly. And those vacuum tube computers are pretty slow. And the electrons in these things are not going through a vacuum, I'm sorry. They're going through silicon, they're going through copper, they're going through aluminum. And if you're going through a conductor like copper or aluminum, you might get a third of the speed of light. That's still not that bad. It's about like this. That's as big as a chip, right? Except if you're inside a transistor, you're about 3% the speed of light. And so you're taking forever in terms of clock rate to get across your chip. And that's just the physics. Once you get past the physics, you got mathematics. You got to have protocols to make sure the data gets understood correctly at the other side and responded to and changes state correctly, and that adds extra layers of overhead. So, the hardware guys, it may be very inconvenient what they're doing to us, but, the laws of physics are being much more nasty to them than they're being to us. So maybe we need to give some sympathy and maybe see if we can help. So let's just take a look at what the effects this has as kind of cartoony thing. This is kind of the marketing message for CPU clock frequency. Crank it up and we'll go faster. Just run the race, we'll get there. The faster CPU wins, bigger clock rate, everything's wonderful. And until one of them just emits a predicted branch. Problem is, you think, the way you think about it, the way you'd hope it'd work, you got something running at 2 gigahertz or even up to 5 gigahertz, or liquid nitrogen on these guys doing the overclocking, get up to I think they got up to 7 gigahertz a while back, maybe they got higher, I don't know. Haven't tracked it for a while. You think, that's really cool, we got instructions going along, we're getting, at 2 gigahertz, we need 2 instructions per nanosecond, more than that if we're superscalar, one life is wonderful, but that's not really the way they work. It's kind of like there's this ocean or pool of stuff, and the instructions kind of filter in, and sometime later come out the other side. It's all very parallel inside the chip as well. And so the thing is, you've got a lot of branches in the program, and the hardware guys really hate the fact we do that. We have branches all over the place. They'd really like to have straight line code so they can just go charging through it, grab it and throw it in there, hash it up in some group and get it done. But we got these branches, and so they have to predict them. And they're actually, branch predictors are pretty good in general, but sometimes they get it wrong. And when they do, you've got a bunch of work you did assuming you're going to go one way, and then the software just whacks you over the head and goes the other way, and you got to throw it all away and start over. This isn't that bad, though, really. Let's go on some other things. Memory reference. We've got these CPUs running at gigahertz, but it still takes many tens of nanoseconds to get out to main memory. Now, it used to be hundreds of nanoseconds not that long ago. It's gotten better, but it hasn't gotten better as fast as the CPU rates have. And they're still kind of catching up, and they aren't catching up very quickly. So if you have to do a real memory reference going to real memory, life is hard. It's going to take some time. Atomic instructions. Read my, I want to be very clear. This is not necessarily a C++11 atomic operation. Because those might or might not involve read, modify, write atomic instruction, okay, where you're looking at some piece of data, atomically changing it, and putting the result back. And there's a lot of constraints on these things. There's a bunch of optimizations I'll cover later that do not work well with atomic operations because they have to be atomic. It is not nice for other CPUs to see an atomic operation halfway through. That would not be atomic. And so there's extra overhead associated with these, which has, by the way, gotten much better over the decades. These things used to be really painful. Pentium 4 was just a nightmare, okay? But they've gotten better, but still, they cause trouble. Memory barriers. These are fences, and they're needed to restore ordering. We'll get into why you need to, why would you ever do anything out of order in the first place? Well, we've talked a little bit about it with the sea of instructions that kind of get executed in parallel inside the chip. That means things will get out of order. We'll see some other reasons later. If you put a memory barrier, you're saying, hey, the stuff before has to happen first, and then the stuff later, just get it right. And suddenly, the CPU has to do something about that. Now, the hardware designers have gotten really, really, really clever about cheating on this, and we'll talk about that later too, which is mostly to the good. The thing is, though, that these things aren't created equal, and I'm going to switch to C++11 terminology here. Sequential consistency barrier or an atomic operation based on it is going to be expensive. Acquire release and acquire release combination would be cheaper. Consume, if it was implemented the way I'd like it to, maybe we'll get there someday, would be cheaper yet. And relaxed, of course, is on most platforms almost free. Now, this is kind of cartoony again. If you're talking x86, relax, consume, and acquire, in theory anyway, would all be essentially just the instruction, almost zero cost over the ordering. But something like a ARM or a MIPS or a PowerBC would have lightweight barriers that can do the acquire, release, and the consume, except on alpha is just instructions again. But this gives you kind of a rough idea across CPU families of kind of sort of what to expect. Okay, now if I hit the right button, a much worse one. These other ones were bad. This one's much worse. The reason that the CPUs can move along reasonably well is that they have caches and can keep the data close. As we said earlier, if you have to actually go to memory, that's hard. If you keep it in the caches, that's fine. But if the data you need isn't in the cache, it's either in memory in somebody else's cache, well, when you see the one CPU in front has his memory in his cache, is doing happy, and is snarking off at the CPU that's got to pay the cost of the cache miss. And if you think that's bad, try I/O. I mean, you know, a cache miss might consume a few hundred nanoseconds or maybe a small number of microseconds on a really, really big machine. If you're using rotating Rust, you know, the standard spinning disks, those things have been milliseconds, you know, several orders of magnitude worse. SSD, solid-state disks, make that a little bit better, quite a bit better actually. But even so, if you're using networking, you know, if you're talking from here to, I don't know, Bangalore, India, well, I'm sorry, but that's going to cost you 100 milliseconds just by speed of light, okay? Let alone going through glass and being amplified and switched and everything else. So I/O can be painful, and there's a whole, that's why there's this cottage industry and things like memcached and other things like that to try to localize things and avoid the need for unnecessary I/O. So I'm going to do this slide, and then I think it's going to be time for break. Let me just take a look and see if yes, we're going to do that. So this is where we're going to stop. This just kind of goes through cost of operations on a fairly old, but not that old system. And the operations aren't exactly lined up with the previous things because it's difficult to separate out how much is due to branch prediction, how much is due to that to the other. So I basically looked at going across threads in a core, across cores, and across sockets for the most part. And I also looked at CAS versus locking for the simple cases. So this particular system had a clock period of 400 picoseconds, 0.4 nanoseconds. And so we have the operations on the left, we have the cost in nanoseconds down the middle, and the ratio to the clock period. In other words, the number of clock periods required to complete the operation down the right. And of course, hardware is going to vary. You can take your hardware, you get different numbers, and somebody else take their hardware, get different numbers. That's fine. This is more or less representative. The key point, if you're just doing normal instructions, you should be able to crank them out at more than one per clock. If you're doing well, maybe one every second clock if you're not doing quite as well. If you are doing complicated operations like compare and swap, which is a read, modify, write atomic operation that we saw the CPU tripping over back there with the electron crowd around his foot, or a locking, you're taking more than an order of magnitude hit for that. That's costing you because the CPU is having to deal with that. Now, this is a fairly old CPU. Newer CPUs might get you a little bit better, but it's not going to be perfect. Cache misses. If you're within a core, one thread to the other, it's not too bad still. You're over an order of magnitude, but not 2 orders of magnitude. If you're going from one core to another within the same piece of silicon, you're almost 2 orders of magnitude. So just having the data flow from one CPU to another, from one core to another within the same chip, within the same socket, is almost 2 orders of magnitude more expensive than a clock cycle. And if you're going off socket, you're well over 2 orders of magnitude. So this really does matter. You've got to be careful. If you spend a cache miss to go off socket, you'd better be doing a bunch of other stuff to make up for that. Because just do the multiplication. If every other instruction is a cache miss, you're taking a 200 times slowdown. That means that your parallel application needs 200 CPUs to keep up with one CPU. I don't know about you guys, but the idea I had when adding more CPUs to make it go faster, not slower. And so when we come back from break, I think break starts about now, it's 15 minutes, if I got that right. I'll take a little bit of a look at what we can do about that. And after that, Magid will take us through a given algorithm to show exactly how he did it for that particular algorithm. Thank you very much for your time and attention. Enjoy break. See you back here in 15 minutes.